This is part 2 of the 5.01 Reaction Rates and Energy. Reactant molecules must have activation energy to form products. Now turn your attention to aspects of the chemical system rather than the individual particles. Temperature is a measure of the average kinetic energy of molecules in a system. The graph shows the distribution of the number of particles at a given temperature compared to the speed or energy of those particles. Many reactant molecules have energies lower than the activation energy, but a few have energies that are greater than the activation energy. Reactant molecules with energies greater than or equal to the activation energy will form the transition state and proceed to form products, whereas those with energies less than the activation energy will not react. Chemical reactions with low activation energies will have more reactant molecules that will form the transition state and proceed to product than reactions with high activation energy. So only a percentage of the reactants will actually form the products. On this graph, you will see that it is those with the needed activation energy. So the number of particles, not enough energy to react, and then enough energy to react. So I added to our notes that E sub A is activation energy, and chemical reactions with a low activation energy will have more reactant molecules that form the transition state and proceed to product than reactants with high activation energy. In other words, look at this. If it's low, it's easier. Easier means more is going to happen. If it has a high activation energy, there's going to be fewer molecules that have enough energy to do that in order to turn into the products. Reaction rates are related to activation energy. What is a rate of reaction when talking about the chemical system as a whole? Rates of reaction are measurements of how quickly or slowly a chemical reaction system will proceed. So far, you have seen how individual molecules react with one another. That forms the basis for how an entire system or a large number of reactions will occur. When we talk about the rate of a chemical reaction in this course, we talk in most cases about a system of identical chemical reactions. A rate of reaction is defined as either of the following: the time it takes for the concentration of the reactants to decrease because they're turning into products, or the time it takes for concentration of products to increase. It means the same thing. It means, look, we're getting less and less reactants. Why? Because those reactants are turning to more and more products. Rates of reaction in systems can be as fast as a fraction of a second or as slow as days or years. So the reaction rate is a measure of how fast the reactants and products reach stable concentrations. In other words, over time, reactants turn into products. Concentration is a fancy way of saying how many. So I start out with no products and lots of reactants. All my reactants, I'm getting less and less and less reactants because they're turning into more and more and more products. Reactants turn into products as shown in the graph. So increase in products because we have a decrease in reactants because the reactants turn into products. How can you increase reaction rates? According to collision theory, any factor that can cause more collisions of reactant molecules or cause more molecules to have energy greater than the activation energy will increase the rate of reaction of the system as a whole. So what types of factors can they be? Number 1, concentration. If more reactant molecules are crowded together in the same volume, the frequency of collisions will increase. Number 2, temperature. Increasing temperature increases the average kinetic energy of the reactant molecules. More collisions means more molecules with energies greater than the activation energy. Number 3, particle size. Smaller particles have greater surface area for more collisions. Number 4, pressure. Higher pressure forces reactant molecules closer together and increases the frequency of collision. Number 5, a catalyst. A catalyst is a certain chemical, and it increases the rate of a system's reaction without being used up itself. Okay, so high concentration. There's more of them. You're going to have more hitting each other. Therefore, you're going to have more reactions and more reactants turning into products. Higher temperature. They're moving faster. They're going to hit each other more. More collisions, more reactions. Surface area. Here they can only hit the outside. Okay, only the outside. So these inner molecules are never going to be touched. Here I have more outside molecules. I only have 1, 2, 3 inside molecules instead of 1, 2, 3, 4, 5, 6, 7 inside molecules. So smaller pieces, more edges, more surface area, more reaction. And pressure. So pressure means I'm forcing it down, and therefore they have to run into each other more. Okay, so I'm just going to copy paste all that into the notes because it was written pretty well. And you do need to know those. So make sure you know it's concentration, temperature, particle size, pressure, and catalyst. So a catalyst is a certain chemical. Okay, so it's an extra chemical that we add that helps the reaction go faster. And how catalysts work is they actually lower the activation energy. A catalyst is defined as a substance that speeds up a chemical reaction without being produced or consumed in the reaction. So it just helps. It does not turn into anything else. That's important. So that's what they mean by without being used up. So the catalyst does not turn into something else. A catalyst does this by lowering the activation energy of the chemical reaction. Look at the distribution of reactant molecules versus energy of a system before and after the addition of the catalyst. Okay, so number of particles, energy. Catalysts allow more reactants to become products by reducing the energy needed, giving the process a boost. So there's not enough energy to react. There's more if there's a catalyst. Only the blue react if there's no catalyst. Before the catalyst, there is a certain activation energy, and a small percentage of the reactant molecules have energies greater than the activation energy to proceed to transition state and product. After the catalyst, at the lower activation energy, a higher percentage of reactant molecules have energies greater than the activation energy to proceed to product. So the rate of reaction is greater with a catalyst. Personally, I don't like the picture they chose because here's the main idea. Catalysts lower the activation energy. Okay, so this is what our reaction looked like originally, whereas if we have a catalyst, now it's going to look like this. See how my activation energy is lower? Because now I only need this much difference instead of the dotted line. Okay, so with a catalyst, I have a lower activation energy, so I only need this much energy instead of all that energy, and then the reaction proceeds. So I think this is a much better diagram. So if we add a little bit of a note to that one, so the catalyst is the blue line, so less energy is needed for the reaction to occur, or a lower activation energy as shown by the blue arrow. Reactant molecules collide together in reactions. Those reactant molecules colliding with sufficient speed, kinetic energy, and orientation, so remember they have to be facing the right direction, will form an activated complex, or a big blob in the transition state, that will separate into products. Sufficient speed is necessary to overcome the activation energy of the reaction. Reactions with low activation energy are more likely to proceed than those with high activation energy. So again, that's why we use a catalyst to lower that activation energy. The reaction rate of a system is the decrease in reactant concentration over time or the increase in product concentration over time, which is the same thing because the reactants turn into the products. Any factor that increases the frequency of reactant collisions increases the energy of collisions or lowers the activation energy, will increase reaction rate. Chemical reaction time it takes is reaction rate. It begins with reactants becoming the activated complex during the transition state, and then of course becomes products. So if I were you, I would just take this whole last slide and put it to your notes as your last review. Again, make sure you go through these. Use the computer to your advantage. Tonight, go through and put little boxes, kind of like you're whiting out stuff. Then tomorrow, read through it and be like, oh yeah, I know that word is reactant molecules. So use it to help you practice. Okay, as always, if you have questions, let me know.